lecture. And also the last day for you to prepare your presentation for tomorrow. Okay, so today I will rapidly explain you the last part of my talk about the size model, and then we will try to make some simulation of some of the model we have seen during my class. Okay, so maybe first what you can do, so go to the website of the school, you go to the document. So in the document you will find all the lecture notes. So I will add the last lecture notes. Yesterday I will put it. And we will also, so if you agree with that, we will also share what you have done for the mini project on this web page. So like that, everybody can use what you have done. Okay, so just go there and download the code for today. I prepare some file, so it's not complete, but you can download it. Just to prepare. So we do some with Python and the rest with FreeFM, just to prepare the last class in FreeFM. Okay, so when you are downloading this, so I will just talk briefly about the size structural model. Okay, so size structural, so I can do it rapidly. So there's again three types of model. One is the matrix model, one we use the mass action law, and the rest is the continuous model. So the matrix model is exactly the same thing that we have done for H. So if you remember, with the H we have H0, H1, H2, and we have with this matrix and the Leslie matrix. So for size, we have to think exactly the same. But instead of saying H, you are thinking about size or different stage of development. Okay, so here I put an example for a tree. So mainly it's based on here what we do. So if you remember this matrix, I told you the matrix is just a translation of what we call the survival table. Okay, so the left-covering matrix is exactly the same, but instead of having the survival table, you have the life cycle. So here the simplified life cycle of a tree or a plant. So you start with the seed, very small, then it can become seedling, then become a tree, the tree gives flower, flower gives fruit, and fruit gives seed. Okay. So if you forget this row, this one, it is exactly the same as the Leslie matrix. Okay, you go, and then you have the birth rate. Okay, so it's a little bit more complicated because you can imagine. So you will stay basically, not necessarily become a tree. Not all the tree will give flower. So you remain a tree, or flower. When you have no more flower, you come back to a simple tree. So you have a little bit more error. But you can do exactly what we have done last time. So you compute, for example, the number of seeds. So the number of seeds here is the number of birds coming from fruit. Number of seedlings. Who are the seedling? So here, the seeds who become seedling, or seeds who survive, if I take the same one as before, plus the one who remains seeds. Okay, what are the three? So tree is seedling who becomes tree, 3 that remains 3, and you have also this arrow, so 3 with flower, coming back to 3 without flower. Okay? So you follow all of this thing, you write a computation, and you get this kind of matrix. So more generally, so instead of having H0, H1, H3, put your life cycle, you choose an order what you want. So you give stage 1, stage 0, stage 1, stage 2, etc. So the matrix is more or less the same as before. So I should put some color on that. So if you want to compute the population at time t plus 1, just the matrix multiplied by n. And the matrix is very similar to the H. So if I do Q and R, it's exactly the same. So you put the verse here, the survival below the diagonal. In the diagonal you have the stagnation, so you remain in the state. Here you have the retroaction, you just come back in one arrow, and you can continue like that. Yeah, it's true if, for example, if I come back and, for example, if I say from here you can come back here, you add another diagonal. Okay, so maybe it can be seen like the blessing matrix, or from your compartmental model, you choose a model, and you maybe look what is going from one point or one patch to another patch. So, like we have done for the meta population model. So the matrix is a bit more complicated, so you have more things in the matrix. So in AC matrix like a lot of 0, here you have a little bit more things, but we can do exactly the same thing. So you can look only on the dominant eigenvalue as before, and you have exactly the same behavior. So you just need to know the dominant eigenvalue to know everything. So it's a little bit more complicated to compute the basic convolution numbers or not. Okay? So if you don't remember how we put reference, but it's exactly the same as we have done for the. So sorry, I go a little bit fast, so like that you can code a little bit. Okay. So the other kind of model for size is using the mass action law. Okay, we have seen also during the school many times the mass action law. So how it works. So now we come back to the King's theory. So you imagine you have an aggregate with I molecule, another aggregate with T molecule, and you put them together. Okay? So what does it mean? For example, here I have 3 molecules and 2. If I take 3 plus 2, I have something with 5 molecules. Okay? My plot is good. Okay, so more generally, if I have something of size I plus something of size G, when they come together, you do something of size I plus G. Okay, you write exactly as we did last week, as some people are doing in the project, just write the mass action. Okay, so you have just take a different notation like I could see from the density of the molecule or the concentration of the molecule or the expression of the gene. So last week we put a bracket here. Sometimes C, so let's call C of L the density of molecular size L. Okay? Attach. And if you write the mass action law, so just to simplify, let's assume we just have 2 particles. So exactly like we did before. So what gives the mass action law? It says so the plus here becomes the multiplication. Okay? So the derivative of this concentration, the particle of size I plus G, is particle of size I multiplied by concentration of particle of size I multiplied by concentration of particle of size G. Okay? But now I have to do that for all particles of the system. Okay, not for all I and all G. Okay, so what does it mean? So if I rewrite like that. So what are the particles of size M? This is all the particles of the system. When you have I plus G is equal to M. So I think I have something there. Yeah, so to get the particle of size M, don't forget this part. So what is particle of size M is, for example, F1 plus Fn minus 1. Okay, F2 plus Fn minus 2. But this is also the other way, so it's also M2 plus F2. Okay, so you take all the combination. So it will give you this part, so that's why you have the 1/2 because you got the 2 terms, but okay, what you say. So you take the particle of size M minus K plus the particle of size K, so M minus K plus K will be M, so the particle of size M, and you have the integrate to do that. Okay? So now I have my particle of size M, but this particle can also aggregate with the other particle, all the particles in the system. So this particle now will aggregate with all the particles. So it will need another particle of size M plus M. Okay? So I need to add this in my equation, so I will add minus. So because now we are not anymore of size M, so I say minus the particle of size M who aggregates with another particle. Okay? And now we have a system of differential equations for Sn prime for all M that verify this equation. Okay, so be careful, it's going to plus infinity. So it's a bit more complicated. Of course, when we try, we will not do plus infinity. Okay, so this part of the model is what we call the coagulation or the aggregation of particles. And then you have the other process, so the fragmentation of particles. Okay, if I come back in my here, so I will look to the opposite. I have a particle of I plus G, and this particle, this group of this aggregate of particle will split into two smaller aggregates. Okay, we break the aggregate. Okay, it will be exactly the same. So what are the particles of size M? So it was the particle of M plus M. So you have a particle, a big particle. This particle will break in one particle of size M plus the rest. Okay, is plus M plus L. So B is the kinetic rate of the fragmentation, so give you something of size M plus something of size M. Okay, so this part, we are going to this part in the equation, it means okay. So is there. So particle of size M plus L will break to give something of size M. Okay? But then also do the opposite. So this particle of size M can also be broken to give two new particles. So I have M plus L. It's broke, give M plus something. But this new aggregate will also be broken, give M minus K, and okay, and then I have to write the equation for all of this. Here I have this new equation only for the fragmentation of the particle. So if I combine everything, the coagulation and the fragmentation, so we get this system of ordinary differential equation. So infinite system of differential equation. So M starts from 1 to plus infinity, and for each M you have to solve the differential equation. Okay, but be careful. The equation depends on this non-linear. So you have multiplication there, and it depends. So the equation on N depends on all the other variables. Okay, so totally non-linear. Okay, not just two particles, you react with all the particles. Okay, so I will not insist a lot on how you deal with this kind of differential equation, but mainly the trick is to rewrite this. So actually it looks like a T, but it's more like a P. So the thing is to rewrite all this equation as a system of this form. So like for the OT, what we like is to do something linear plus something digits, locally digits. But here the difference is A is not a matrix, it's an operator. But if this operator has good properties, so here the property generator is very good, forget that. And if F is locally digits, you can do everything more. But sometimes the operator A is a bit complicated. It's not so easy to prove that you have this kind of property. Okay, but maybe the idea, you have a system of infinite system of equation, and you write as a bit. Okay, so just to prove that, it will take us one is possible. Okay, one application for blood clotting. So blood clotting, what is blood clotting? So if you remember my talk in the first day. So you can use. So when you are bleeding, so something will activate the coagulation process. So we call A to simplify. So this is the thrombin. So we activate the coagulation process. You have an inhibitor. So one of the inhibitors is serpin, for example, his job is to reduce the coagulation process or to accelerate the fragmentation. And you write the mass action law, it's a bit more complicated, and you will get this kind of differential equation. So, for example, if I put A equal 1, I don't put 2, I put 1 here, find again the mechanism kinetic here. Some degradation, the degradation of A, the competition with the inhibitor, and the inhibitor stop, and some growth or activation rate. So here you have a tool, so a little bit more general than what you have seen before. So it's something of this type, so I remember well, so I think group 1, something like that, in their model. Okay, then you have the question of the inhibitor. So here, so the inhibitor depends on the activator. So the more you have activator, the more you need inhibitor. Maybe. So the logistic equation, some critical value, and here a process and the degradation. Okay, so it will activate the process. So what A is doing. So again, this is the latte, but if you remember, if you want to do good modeling for S and biology, you need to know a little bit of biology, medicine. So what do the activator, the thrombin, it will transform what we call fibrinogen into monomer. So it means you have now one solid particle, and so it transforms this chemical species into something else. Okay, so this is what we wrote. I'm looking at the concentration law, again, the concentration of this guy. So will be transformed by the activator, and here, so maybe I should write the plus, the opposite, so it looks more. So if I put in the overweight, what does it mean? The fibrinogen, so if you forget that, you go to the equilibrium, the maximum quantity you can have. Okay, so this one is just close to the quantum. Okay, so now we have particle monomer. Monomer means they are particle of size 1. Okay, monomer is one particle of size 1. Okay, and this particle got to coagulate. Okay, again, so you have the activator, the chemical species. We start the coagulation process, so it transforms fibrinogen in a monomer, and then the monomer will coagulate. Very good. So, okay, so particles of size 1 are the monomer. So particles of size 1 are created by the fibrinogen and the activator. Okay. And then you rewrite the equation you just have seen. So particle of size 1. So one particle of size 1 will aggregate with particle of size n. We have a new particle of size n plus 1. And the bigger particle of size n plus 1, they can broke or fragment with again a particle of size 1. Okay, so I have particle of size 1, they can coagulate with bigger particle. Okay, this is this one. But bigger particle, they can also fragment to give again a particle of size 1. And then you write all the equations for all the different sizes. So it is exactly the same equation as before. The only thing that changes is the first one. So it starts from the beginning, the activation. Okay, at the end you have this kind of equation for the plot. Okay, of course, so it means so I have at the end 1, 2, 3 equations for the biochemical part, and I have one equation for the monomer, an infinite system for all the other sides. Of course, in the human body, so you don't have particle of infinite size. So what does it mean? When you will simulate that, so you cannot make the till infinity. You can give for the maximum size of particle, stop it. So, but usually, so when you want to solve that, the good thing is, as you have done last day for the edge, okay, we say edge, so we start like that, so edge plus 1, so we celebrate Thursday every day. So in the Silpakorn, we celebrate Thursday every day. But as the edge, size is actually a continuous process. So you grow, and fragment. It's not totally a great process. Okay, so you can do exactly what you have done last time, so I will not insist. But you start with the matrix model, but instead of saying I'm going from one stage to the stage, I say I'm going from one stage, so take n plus delta n. Going step by step the base one. And then I make the step go to 0, take the limit, and we get this kind of equation. So this is exactly the same equation as the h. So just change the notation of n instead of a. Get it a if you want, get it x if you want, it's not a big deal. So exactly the same equation. So, but here the growth is there actually for h. I have function value p, but actually it can be also inside. But what does it mean? It means exactly the same as the F, so it means the population will grow with this rate, the G of I, depending on the state. And here you have the degradation or the reduction of the size. Okay, but exactly the same type of equation, but here is if I start for the matrix model. So what happens if I start for this one? So you do exactly the same, so instead of saying okay, I'm going from minus instead of saying I'm going from n to n plus n, you say n plus delta n. Okay, you grow small. Then you divide by delta n. You take the limit when delta n goes to 0, and what you get, so this term will become an integral. And you will get this kind of system. So you will get now this. So this is the PDE actually. So this is the PDE. So instead of having the sum line of the integral from 0 to n, the coagulation process, the fragmentation, and the other part of the coagulation and the fragmentation. Okay, so exercise, try to write this equation in this form. Actually, it's possible. So I think there's 2 students here who are working on that. Yeah, let's see my face. So maybe if you don't know how to write this like this, then explain it. When you did that, how you call it like this. And so sometimes, write like a PDE, this form is also very good in terms of numerical computing. Because there is this method to solve that. So, for example, free term is not good to solve this kind of equation. So this is a conservation law, math equation. And for that, you need to use what we call it's better to use something that conserves the mass, because it's a conservative equation. And it's better to use finite volume method. The finite element method, like in free term, you can write this in free term. We will not have time to do this, but the result will be 1. Okay? So again, this is can be a topic for another CIMPA school, how we solve this kind of equation. And one thing maybe I can also explain you why it's also very important for you as a mathematician to understand that. So, when I started working with some, let's say, experts in biology, chemistry, etc., and you will see also on tomorrow there's some people in group 7 where we will show you a software to solve the equation. Very easy, you write the equation like it is. Don't care about how you solve it, just write the equation. So, for example, so you see tomorrow, I will show you. You write the equation and you click run, give you the result. Okay, for ODE, simple ODE, it works. And even for some ODE, it doesn't work. But for PDE, so there's this software, PDE, you write the equation like that, you click run, and give you the result. Once I was with a group of biologists and chemists, they did that in front of me and told them everything is wrong. And everything works. Okay, because this kind of software is because they use the software without knowing what is inside the software, they use that as a black box. So it's very convenient, but you don't know how to do it, okay, to try. But if you know what is inside the software, you know that this is not possible to solve particularly this kind of equation. Of course, the software always gives you a result. But the result was totally wrong. Of course, they publish like that. So if you don't publish in mathematics, nobody will notice that. And I told them if you write this in a journal of mathematics, of course, impact factor is less, but they will tell you that everything pattern is wrong. Okay, so this is important for you as a mathematician, of course, so you need the help of critical vector values to build your model, but it's also important for you to say, okay, this kind of equation, I can solve it with Physical, I can use it to find the difference, I can use with Python, and that. Okay, so I also saw that a lot of you are using, for example, MATLAB and OD45. I will find example if you want that OD45 gives you wrong result. And I can tell you for most of the problems coming from biochemistry, results coming from OD45 are wrong. So I have no time to make a class on the numerical methods for ODE and PDE, but there is something inside that you cannot, again, ODE45 is one shooter of order 4 or order 5. So order 4 or 5 is the good method, but it's not suitable for most of the problems coming from biochemistry. Everything is wrong. Okay, that's why also I prefer to use Python. So because MATLAB, you don't know exactly what is written in ODE45, if you are not, let's say, expert of what they put inside. And actually, so that you are not supposed to know what they put. The solver of Python we will use now, so you know exactly what is inside, and the solver of Python has something inside to avoid the problem of ODE45. Okay, for example, if you don't know anything, you will fit with the solver of Python, you will select the best method for you. So if you check first what we call the stiffness of your equation, make a computation first, and then you choose the best method. So it's not so you can ask him, okay, use the one shooter 45 if you want. But it's better to let him choose for you. Because you will select always the best method for you. Okay. Do you have any question on that? So we could also reference and everything. Meaning A are functional. Yeah, now it's functional. Okay, the simplest case is when A and B are constant. But even in that case, it's not so simple to do that. But in general, A and B are functional. How to define it is also complicated. It depends on the particle, how the particles are connected or not. No, to get this A and B function is more on the fundamental biology, depending on the particle, how they connect together. If they connect 1 by 1, they connect 2 by 2, 4 by 4, sometimes 8 by 8. So it's like that you know the law function. Or how they split also. So this is what we call the piping process of the cell, how they connect together to give you the function A. And it's not so simple to get this, especially if you are breathing in the lab, okay, but in the real human, or it's not so easy to get this function. So usually, if you are doing mathematics, you do function that you can make mathematics, but when you are dealing with real things, much more complicated. So because in reality, you have different functions for the same problem. You can have some particle will collect 2 by 2, but some for the same species will collect 4 by 4. Very complicated process. Okay, so let's try to make some simulation. So succeed to download the code? Yes? Okay? Like that? Okay for you? Have you been the code? No? Yes, no? No? So you go to the web page, go to the document, so everything will be on the page. Okay, and if you already download, maybe you can open there's something structured model to the notebook. Change the color. Okay, just download and you have a file, so the file is. So I already put the main library, but not all the solution. Try to open also. Yes, succeed to open it. Yes, so this is the notebook here. So the notebook have, so this is the VS Code. So VS Code is a good editor. You can also use it for Fusion. It's now also a library for Fusion. So this is the notebook, or you open it with Jupyter Notebook if you want. This is again for anyway. Not a big deal, you will run it for okay, so I put the main library. So the difficulty with Python, because with Python you can do everything you want. Of course you can do mathematics, you can do data processing, you can do image processing, you can do web, you can do software, you can do game, you can do almost everything you want with Python. So the difficult part in Python is to find a good library. But especially for mathematics, what you need is NumPy and Matplotlib. NumPy is the main one of Python, and Matplotlib is for the graph. You see what, or should I do? Okay, so NumPy plus Matplotlib, this is MATLAB. You have all the MATLAB, and then you have CIMPA, Scientific Python, and this is the two box. Okay, if you fill in MATLAB, so NumPy, Matplotlib, MATLAB, CIMPA is the two box. So here what we'll not do everything, so I think I just plan to do the ODE part. So the solver for the ODE is inside Cycling Integrate, and inside you have the ODE solver. ODE Integrate. Integrate the differential equation. Okay. So here's the Matplotlib is to make it a little bit nicer. Illustrate if it works. Okay, then you can just run the two. Okay, well, this command is the best. Yeah, so here there's a this PLT. So these two commands is just to have a nicer picture, not very important. Okay, I import what I need. And let's try to make first the meta population model. You open meta population model. Split. Okay. Okay, so the meta population. Okay, everybody can load the library in the computer. So you cannot, I think in your computer you have Anaconda installed already, and you can just open the details on it. Yes, okay. Okay, let's try to make this one, the SIR. The SIR model. So here I just take some random value, so just to play, not to make something realistic. So let's try with 3 patch. So why not? Okay, so we just add this command. Okay, so if you can just add this. Okay, so it depends on the version of my computer, looking at the same. So I just to have some random number. So round M is just the normal distribution. Okay, and just taking some random value for all the parameters here. So for the here also put mortality. But have the new, so beta is something under, gamma constant under, and I take also mortality but each patch. Okay? So it's just the parameter in the equation, not the beta, gamma, and here you can add also. So let's remove this part. We just have, here we just have two parameters, okay, but beta and gamma. And let's take gamma. Okay, I have three patches. So what I need now is the connectivity matrix. Okay, I have three patches, they are, I assume that they are all connected. So what I need is this matrix G. Okay, if you remember the matrix, the three patch. So the G is here. Okay, this is arrow. Okay, so I need a 3x3 matrix. Okay. Okay, I'm taking something random just to try. So now I have my matrix, my 3x3 matrix. Okay. Maybe I want to avoid. Maybe we can plus 1. So just to have something positive. Okay. If I just put 1 and okay, that's why I put. Okay. Now I remember why I put 1 and okay. So just okay, yeah. Okay, so 1n is the normal distribution, centered at 0. So that means you can have negative value. Okay, and 1 is just taking value between 0 and 1. Okay, so that's why okay, we can forget also. Okay, so just before, so let me try again. If I put here with the normal load, so here you see you have negative values. Okay, but the connectivity matrix is only positive value. Okay, or non-negative value. It can be 0, but it cannot be negative. Okay, so here just in terms of so yeah, so this is one source of error, for example. Okay, you write over there, the connectivity matrix is positive, but when you code, you make the same mistake as me. So it is, instead of having positive value, you have negative value. So when you will run it, it will give result, but the results are wrong, has no biological meaning. So it cannot be negative. Okay, that's why I changed, I remove just the n here. So like that, I have the number between 0 and 1. Okay, I can multiply by 10. Okay, everybody has the parameter and the matrix? Yes, okay. Okay. The end point is okay. Perfect. Looks good. Okay. So we have got the parameter. So let's try to write the equation. So you see Python is also like in math, very easy. So I need to define my equation. Or maybe I should change it. Or D1 or S alpha, beta alpha. We give the name you want, and it's always like that. So the definition of differential equation in Python is always like that. So the variable and the time. The first variable is less time. So if you want to get add parameter after that, the first is always the variable and the time. Okay, and then to simplify, to make it easy, you say, what is your variable? So let's say I have 3 patch. So 3 patch. So my variable, what are my variables? S0, I0, first patch, S1, S2, second patch, S2 and 3, third patch. Okay? So, to simplify, I write okay, S0, I0, S1. Okay? And you need to, if you choose this order, you need to keep this order. Okay? If you want to write S0, S1, S2, I0, I1, I2, you can. But remember you that you put first the susceptible, then the effective. Okay? Order is very important. But the name is not so important. Okay, then you write the equation. You write exactly what you see. Okay, so S0 dot, S0 prime, the verb. What do you prefer, dot, prime? Dot, okay? And you write the equation. So start writing. Okay, you write minus beta multiplied by I0 multiplied by S0. So maybe first we can just write the connectivity. Okay, try it. So I can add. Let me try also the first one with you. Or minus. So that's why I did that, so like that I give exactly the name in my paper. Okay, so like that is very easy. I give the same name in my computer. So no mistake like that. So beta, multiply by S0 multiply by sorry, I0. Everything the same. I0. Okay, then we will add the rest later. And the second line, beta, and copy and paste. Beta plus beta. Okay, one important remark in Python also for the coding. So don't change the form. Okay, if you put there, it means I am inside the function. Okay, if you do something like this, yeah, maybe too much, but it's not important. So for example, if I do something like this, I'm not anymore in the function. You will send error. Okay, so you have to keep the indentation is very important in Python. Okay, also it makes your code nicer. When you read the code, it's easier to read. Okay, in MATLAB you can do this kind. In Python for okay, for my first and not forget minus gamma multiplied by 0. Yes? Then you can copy and pass for 1 and 2. You just send. Okay. Then here is 1, 2 and 2. So you can just make copy and paste and press. Or maybe you can just start running the code like that. Okay, at the end I give my equation. So I give all the derivative. Here I give S0 prime, S0 the day. Okay? So you can, so for the meta part, you can just run it to see it works. So you can run the rest. I already give the final time, enough information. The initial data, we start with 100 people in patch 1, 50 susceptible in patch 2, 150 in patch 3. So you just need to run it and solve the equation. We have changed the name. So if you change the name, like me, here change the name also. Okay. One remark, so because some of you the code failed and they ask me why it's failed. And in Python you just need to read, it's written why it's failed. So sometimes it's complicated, but most of the times. So it could be error because the function is notified. So you just need why it's notified. Okay, because I just changed the name. Okay, so before asking, just read what it told you. Okay, now I solve the equation for current U, and inside U, I have S0, I0, S1. Okay, and then you can just plot it and see. Oh, sorry, I put 0 and I'll change it. And then you can plot it. Okay, just to see if it works. So probably you don't have exactly the same as me, but this is normal because we choose random parameter. So I hope we don't have all the same. Okay, normally if you check the label, it's not exactly the same. Okay, it works like that? Yes? Okay, so now let's try to add the connectivity part. Okay, so of course, so we can do simpler than what I will do, but let's write everything. Okay, so for the first patch, you have to write everything that is coming from the other patch going inside. Okay, so you write. So what is coming inside the patch? So I have plus, so I will have people from patch 1 plus people from the patch 2. Okay, but I need to add the connectivity. Maybe again, you want to use it? Better like that? Okay, people from S1. But I have to multiply by the connectivity method, so G. So the people who have 1 is coming is patch 0. 1, comma, 0. Key is exactly the same notation, so it's, I was in 1 and I arrived in 0. Okay, you write exactly what is written in. So it depends. So for ODE, simple code, you don't need to make the best code of your life. You don't need to have a big performance. Of course, if you are doing complicated things with spread and size, maybe it will put this kind of computation. So it is the same. So the people who have 2 and come in 0. Okay? And now I have to compute the people who were in 0 and living somewhere else. Okay, so now I have the minus. So people who are in 0 and going to 1. And then the same. And people in 0 going into. Yes? Okay, you write exactly what you said, okay? People who are in 1 go coming 0, who are in 2 coming 0, and the one are in 0, where you are, and you do the same for the infected. You just need to copy and change the S by I. Okay, and now we do the same for the second patch. Okay, again, we copy. So second patch, you have people who are in 0 and arrive in 1, and then you have people who are in 2 coming in 1. So minus, so the people who are in 1 they go to 0, and people who are in 1 going to 2. Okay, copy. Just change. Okay, so in the last part. Okay, so now I have people who are in 0 arriving in 2, people who are in 1 arriving in 2, minus people in 2 going to 0, people in 2 going to 1. Okay? So if you write it slowly, it's not too much complicated. Of course, if you have a 1,000 or 7,000 patch, you will do it like that, of course. So a very simple way to write this multiplication, of course. And just to learn, if you have few patch, okay, you can write it. Okay. Again, if your model is well written, put it in the computer, it's not so complicated. Totally write it. Write exactly what you need. Okay, then you can run it again. Let's see, here for me I have this thing, so it's a bit different, so people are, so you see people, so depending on the matrix also. So in my case, people, most of infected are patch 1 and 3, no, patch 2, yes. Okay, so they, so you have, it's one for you? Yeah. Okay. You the code with the correction drive. Just try together at least. You probably have the make a mistake. So normally, the model you can prove that everything is positive. So if you have something negative, so this is okay, so when you have a lot of things like that, be careful with what is plus and what is minus. Normally the slide for the SIR plus, so the solution should be positive, or at least not negative. You can have 0. Okay, you have something. You are too far from me. Okay, nice. You can do it with Julia if you want. Julia, Nathan, what you want. Okay? Yes? No? You copy? Okay? Perfect. But don't worry, I will provide the code. Okay, so if you understand how we solve the problem, let's try with the blood clotting, so like that we have some blood clotting. So the second part I already prepared. So let's take some one variable. Okay, you alpha, b, gamma, any parameter, and we'll just do two sides. Monomer and dimer. Size 1, size 2. Okay, and so on. Okay, we do exactly the same. Maybe I will check. can then you do the same now. My parameter with A, S, C1, C2. And then you just copy the model. Okay? Write exactly what is returned there. And you write, okay, let's try to do it together. So I write alpha. So yeah, be careful, so in Python, the power is 2 star. Okay? So if you do this is not the power of Python. Okay? Or sometimes there is some strange thing in Python. But can we write exactly what I see? Is squared. Again, so if your model is well written, no difficulty. Alpha, but guys, be careful with the parentheses and all this thing. Then second one. Instead of looking at that, you should look at that. Because I write exactly the same. I think it's simpler to read here that you see, don't forget the star and that. Read that and write. Yes, see, so if you copy me, it's wrong. This is good. Thank you. Okay, and you see, to simplify everything, all my parameters give exactly the same name as in my model. Okay, so it's simpler way, you don't need to modify all the parameters, don't need to write X, Y, Z, A, B, C. So do you have the two first equations? Yes. So now I need the equation for C1 and C2. So a new right here. For the equation, we start with that. A equal to that is 15. the coagulation process. The particle of size 1 can coagulate with particle of size 1, give something of size 2, and the particle of size 1 can also coagulate with particle of size 2. Okay, they give you something of size 3. Okay, you will stop at 2, so this one will give something that we don't care. Plus, so the particle of size 2 can be fragmented to give particle of size 1. Blood okay, so then the calibration. Okay, and then the particle of size 2 are the particle of size 1 coagulate. The particle of size 2 they can coagulate with particle of size 1. Particle of size 2 can coagulate with particle of size 2. Okay, so we have size 3 now is size 4. Then the breakage. Here, so we stop at 2. So it means we don't have bigger particle that can break into. Here actually the B here we don't have breakage. But only breakage to give smaller particle. Particle of 2. Let's see. Okay. I check the name again. Yes, sorry, my fault. So let's. Okay, it's also good. Good thing. So because in Python, everything starts at 0. Okay, so 1, 1 is the second line, but 2, 2 is not in my matrix. Okay, so I have to put actually 0, 0, 0, 1. So I have to reduce everything of 1. Okay, so because in Python, the table starts at 0. Okay, it's not like so in MATLAB you start counting at 1, Python you start at 0. Okay, that's why I have the. Okay, you can read. So here, okay, index 2 is out of the map. Okay, so because my table is 2 by 2, but since I start at 0, so at 0, 1. Okay, so here I have to correct not 1, 0, 0. Okay, so be careful when you are using Python. This is also source of many errors in Python when you make mistake in the tabulation. So that's why before I start at 0 from there, 0 enough. Okay, good. Ouais. I just need to part the coagulation, the polymer here and the biochemical there. Of course, you can put it the same plot. That's all. Okay. It's working for all of you. More or less like that. And it works nice. Okay, but don't worry, I will put everything on the right. Let me check if my code is correct in my notes. Yeah, nice. Okay, so you see, dealing with the differential equation, items not complicated, and if you want to know what is inside the solver, you can write, you can Google inside pi or it. You have everything about what is inside. Okay, so you have what is inside, how it works. What kind of method you have, everything is different. Okay, so I think most of you know the Euler method to solve the differential equation. So inside Python is what we call predictor-corrector method. Maybe you don't know. Okay, so just one more so you will see the trend. So maybe we'll see maybe doing minor lecture if we have time. So there's also 2 points in freestyle. Maybe you can, if you go fast, you can try to do it after the break. So just try to solve well, at least like that you will have a code on the edge of trying to solve the PTE or solve this equation. Okay, to solve this one, this PTE you have for the biochemical reaction space and also the water. The water model, this one. Okay, you have already two feet. So this is the two frame code. But this is the same you have. Okay. So the initialization. The variational problem. Okay, it works because in the variational program there is no fit. Okay, and how to solve the problem. Okay, so because this is depends on time, so you have to make iteration. So anyway, I will give you also I will give the code with the answer, and you can try after the of my okay. Any questions? It's okay for all of you? What's fine? Okay, so we don't do, I think, Okay, so because we have to come back, it's 10, 15 minutes. Okay, thank you. So if you have any question, okay. Okay, first. Okay, so you want to okay, so then the break is again the 14, and then we come back to that. Okay.